All right. Yeah, welcome back, everybody. Today, I decided to give a talk about one of the works my team has done, and it is about robust reinforcement learning. And of course, it's not going to be only papers from the team being given. We will also be describing other papers, hopefully with corresponding authors who come in and present their work. But today I wanted to discuss a paper which we called Wasserstein Robust Reinforcement Learning, which I think is a very interesting piece of work. And yeah, I just want to tell you what this is doing and how it works. So this is a paper that is co-authored by Mohammed, Hang, myself, Vladimir, Rui Mintiang, as well as Jun Wang. And let's just start by just trying to understand what is the current status of reinforcement learning, just trying to motivate the current status of reinforcement learning, what it's doing, and how do things work. So let's start by understanding why we want to do reinforcement learning, right? So why are we going to do reinforcement learning? Well, we talked about this for a while now, and we talked about it in previous sessions and previous lectures. And then we realized that we can abstract a lot of cool problems, such as driving problems, maybe financial trading problems, logistics, robotics, or computer games. Though they look very different, but they somehow abstract to this shared communality where we have a framework for sequential decision making under uncertainty. So what we have is we have a problem that involves a sequential decision making problem. So agent, right? Remember that. Environment. They talk to each other, and then the agent takes an action, the environment responds by a reward and a successor state, and then based on that, the agent tries to maximize its total discounted return. Now, we discussed briefly before that there are different types of solvers for reinforcement learning, and what I'm going to try to do in this slide is first explain reinforcement learning again, as we did it before, for people who didn't see the other lectures, and then give you a slight recap on some sort of algorithms. So, as we said, we have our agent, which is our brain right here. We have our environment, which is right there. They talk to each other. We take an action, and then we get a reward and a state. And we said that we formalize this as an MDP, and MDP has a state space, action space, transition model telling me how to transition from state to another, and a reward function telling me how good the agent is doing. Now, upon subsequent interactions with the environment, the agent collects a trace or a trajectory, as we said before, and the trace is nothing but a sequence of state action pairs. So we start at some x0 from an initial state distribution. We take an action according to the policy, then I query my transition model, it takes me to a successor state, and then I repeat this process for a horizon of length t. And then my goal is to determine an optimal policy, which is trying to maximize the expected total reward in that environment. Now, we discussed some types of solvers to solve this problem. We talked about model-free and model-based algorithms. And we also talked that some other authors have been able to show that simpler models work very well for these systems. So on a high level, so to say, the reinforcement learning solvers, I like to categorize them in this way. I like to say, okay, for reinforcement learning, we have what we call a model-free type of solvers and model-based type of solvers. And then we also have different types of how you want to access the policy and how it's doing in the environment. So for example, we have the indirect methods. We described them a while ago, or maybe briefly touched on them. And the indirect methods such as deep Q networks and neural field iteration, temporal difference methods, what they do is you give me a policy, you don't try to kind of improve the policy directly, but you indirectly build some sort of a Q function, right? Some sort of a Q function that measures or estimates how good a policy is doing. And then, and then based on that, you just try to improve your policy. Direct methods, on the other hand, for example, there's the policy gradients, which we elaborately described and derived. There's policy gradient with baseline. We didn't touch that on that yet. I will come to that maybe in other videos. And then there's the gradient-free methods. And these gradient-free methods are simply, just do the updates without accessing the gradients, similar to what we talked about in Ben Recht's paper. And there's also hybrid methods, right? So these hybrid methods are actor-critic methods, what people refer to as actor-critic. And honestly, for me at least, it's just a fancy name to say it's a policy gradient with a baseline, but I'm gonna just learn the baseline. But anyways, they're called actor critic, maybe to improve the soundness of the name. And PPO, TRPO are examples of this, and they combine the both worlds, right? So they take they have a actor that takes the actions, and then they have a critic, and that critic measures indirectly how the policy is doing, and then it tries to improve. Now, these methods are typically sample inefficient, as we described before. So there's also the model-based type of solvers, the model-based types of solvers, which I think Pilko is one of the awesome solvers for that. And what Pilko is doing is trying to do a Gaussian process model, and then based on that try to update the policy. And there has been follow-up works on that, like probabilistic MPC and other stuff. Our focus in this work, we're going to be more towards these inefficient methods and not the model-based ones. We have other works concerning the model-based solvers that I will maybe talk about later, but not in this talk. All right. So there has been a lot of success in reinforcement learning, right? So maybe okay, this is the Atari from DeepMind. Then you have heard of AlphaGo. Then you have heard of the robot arm that is trying to deal with these cubes. And then what they do is they try, to fit a network that maps from an image or high dimensional state representation to Q values or directly to actions if you are doing direct policy search. And this how these methods work, and they work really well. Now, there are a couple of problems with these techniques, and based on that, the team's focus that I'm leading has been centered around. And I just want to give you a flavor. Maybe you get interested to join us in some time in the future. But our focus is kind of threefold, right? We're trying to do some what we call learning to optimize, but really it's kind of optimization, like non-convex optimization. And we have some papers on that, such as compositional Adam is one of them. We're also trying to do robust and safe decision making. One of the talks today is going to be about the robustness. And Samba is another work we put out that I will maybe talk about in later future. And then we also have a multi-agent component to our work that we are looking into, and that there's a dedicated sub-team that is doing that. And we're also trying to look into model-based RL a lot. Samba is actually an instantiation of model-based RL, but to safe scenarios. And we also are looking into kind of memory augmentation in order to try to learn options that allows us, to do continual learning and adaptivity in order to go to computer games. So out of all these, what we're going to be discussing today is just a subset of this direction, which is about robustness. All right, good. So now the question you might ask is like, okay, why would we need robustness at all, and how are we going to deal with this robustness, right? Okay. So let me give you a reason for that. At least, so there are many reasons, but this is the way I would like to think about it. So imagine you want to control something in the real world, right? So this is a car, we want to control it in the real world. Because current RL algorithms are very sample intensive, and it's very hard to train in the real environment, it's really difficult to do that. Maybe because of safety considerations as well. Then what we do is we go in this direction, right? So where we now build simulators, right? So there are tons of simulators for self-driving cars. I just give some examples here: Carla, Sumo, and other types of simulators. So these simulators, of course, they're not the real world, right? So these simulators are actually kind of an abstraction, right, of the real world, and they made assumptions and idealizations and stuff like that. But then the goal you build your simulator, apart, from just understanding, a real world phenomenon, what you try to do is you try, to learn in this simulator. So I'm going to just interact with the simulator, not with the real system, all right? And then I'm going to try to learn a policy there. And after I learn a policy there, I hope that my policy goes back to the real system, right? So I try to kind of, let's call it pi simulation, pi sim here. And then you hope that this pi sim is going back, can generalize back to the real world. Now, of course, I'm sure you heard about domain randomization and all that stuff. I will show you later that we actually beat domain randomization in what we did. And I believe domain randomization is a special case of robust learning done in a high variance manner, but that's another discussion. But now the idea is, so let's continue talking about this. So we built the simulation, we trained, and now we want to go back to the real world. Okay. Now we know that the simulation is not exactly the real world, it's some form of an idealization, right? So if we want our loop to work, the one I described, you want these policies here to be kind of robust to changes in the dynamics of the simulation, hoping that at a certain moment, as you change a lot your simulation, you can get somehow close to the real world in a sense, and then your policy would more or less transfer safely to the real world. Now, of course, what we will show later is that none of these RL methods are actually robust, state-of-the-art ones. They're not robust to even teeny tiny changes of the simulation. So now, if we want this loop to, at least to start working, there's tons of other problems I'm not talking about here, but if you just want it to start working, then you need to actually be having some robust type of solvers, such that they work across, slight variations of the dynamics in these simulators. Okay. So now, let us try to understand the state-of-the-art RL, and where it is on this robustness spectrum, right? And when I say a state-of-the-art, I mean methods that are model-free and work in high dimensions, right? I'm not just interested in low-dimensional methods. I want, to work in high dimensions. So what we have done here, this is a slide, right? What it's trying to say is that none of these algorithms are robust. So this is a cart pole problem. So that's a cart pole. You know the cart pole, I'm sure. Right? So what we have done, okay, we have trained a cart pole on the length, I think 1.7. So this is the length you see here, okay? So the length of the pole, we set it to 1.7, all right? And then we trained this cart pole using DDPG, TRPO, and PPO, kind of state-of-the-art methods. And this is us, by the way, WRL squared, WR squared L. We're gonna discuss it in a second. But then what we did is we trained it, okay? We trained this policy, so call it pi 1.7, okay? And then we started testing this policy without further training on varying the pole lengths. So we started changing the pole length, and then, wanted to see what's gonna happen with this pi star, let's say pi star 1.7. Now what you can clearly see, and on the z-axis here, I'm just plotting the mean testing reward. So what you can see is that, okay, DDPG is highly unrobust. A slight change, actually just causes the system to fail. TRPO and PPO, they're kind of robust, but also start failing in these regions, okay? So please note that these regions are really not that far away. It's 1.7, 1.9, it's not that big of a difference. But you might say, well, you know what, yeah, what's the point? Like, it's very small change. Well, what we wanted to convince you with is that this problem becomes even more amplified when you go to higher dimensions. So we looked at a walker, and in Mojoku, the walker is parameterized by actually two parameters. There are 11, so we did the test later, but for now, we decided to vary two parameters. We decided to vary the friction as well as the torso density, okay? And then we trained on this system here. So that was our training system right there. And then we decided to test on systems by varying, the friction and the torso density, all right? So what we have done effectively is this task here, but we've done that in two-dimensional space on a walker. And now the dark red color, so this is a heat map, the darker the color, the higher the reward, and the brighter the color, the lower the reward. So what you can see from this is, again, as we vary, a little bit, then, you start getting very, very poor performance. And now similarly, this is on a hopper. So this is a walker. Now this hopper is just like a hopping robot. I think it just needs to hop. And then you also see upon minor changes, you see bad behavior. So this is like a performance deterioration under minor dynamical variations. And that's problematic, especially if we wanted to kind of, apply this idea, which we discussed before. All right. So what are we going to do about it? How are we going to induce robustness? All right. Now, the funny part is that a lot of work in machine learning is carried over from a lot of other fields without giving credit to the other fields. What I would like to do here is I would like to give a credit to the other field which already studied the robustness problem in decision making, and that was robust optimal control. So if you just search robust optimal control, I think you get 159 million results. And then there are very two nice books about it, okay? So robust optimal control, what it does is it introduces an adversary, okay? So it said, okay, this is my controller of my agent, right? So I want to find the optimal action that minimizes some cost function or maximizes some reward. I'm gonna now introduce an adversary, and that adversary is gonna start, changing some aspect of the dynamics, all right? And here it's like a disturbance addition. And then you try to solve this problem. So you try to find the best performing controller, right? So the best performing controller under the worst case adversary, right? So that's what you do in robust optimal control. I mean, I like to say it like a plan for the worst and hope for the best, in a sense that during learning, what we're gonna do is we're gonna just plan in the worst case if a disturbance happen, if the adversary hits us, if the adversary gives us some bad disturbances. But then what I'm gonna try to do is I'm gonna hope that the aspect where the real environment is not much varying than this system. So then my policy, though can be conservative, still is safe and works robustly in the real system. So this is the idea of robust optimal control. I think there are two components to take from it. The first one is the introduction of an adversary, and the second one is like tweaking, during the learning process, the dynamics model or, the reward function or something like that. So what we're gonna do is we're gonna take this idea and put it in an RL setting with some tweaks and changes to suit RL a little bit better. So what we did is we said, okay, look what we're gonna do now. We're gonna, like this loop here, from a policy to a simulator to gathering traces to an algorithm. This is kind of the standard RL loop, right? You start with a policy, you call your simulator, you apply the actions, you get the traces, then you run your algorithm step PPO to FPO, whatever you would like, and then you get an updated policy, and then you repeat this process, right? That's kind of the standard RL loop. What we are going to do now is we're going to introduce an adversary right here. And that adversary has the power to change and tweak the dynamical model of the environment. All right. So what it is capable of doing is that, okay, while training, the adversary will say, okay, I'm going to now make the length a little bit longer. I'm going to make the length a little bit shorter, and so on. Now, please note that this does not mean that the adversary can change all aspects of this MDP. We just focused on transition model variations in this paper. Now, with that, we can define the following problem analogous to the optimal control problem. We're going to try to find the best policy. So we're going to try to maximize over theta, try to find the best behaving policy. But now we're going to do it under kind of the worst case possible dynamics, right? So we're going to try to say, okay, find me the best policy, but under the worst case possible dynamics that the adversary can do, all right? And the objective function is nothing but the total reward. And now your trajectory tau, rather than it being sampled only from the standard transition density, the transition distribution of trajectories, now this trajectory distribution is actually parameterized by both the adversary's action and the policy itself. So here, what p phi theta means, it's kind of pretty simple. What p phi theta means, so for those of you who've seen the previous lecture, that's nothing but like a p0, right? Then we had a product over xt plus 1 given xt ut, and then we had the policy pi theta of ut given xt. What we effectively introduced here is another phi that is actually capable of changing, the transition dynamics. All right, so far so good, but there's a problem. The problem is that this can lead to arbitrary bad policies, because anytime you make some good move as an agent, then the adversary can give you some arbitrary messed up dynamics that will render your policy useless. So we cannot hope that, without any constraint for this system, we can get some meaningful solution. So in order to guarantee a better behaved optimizer, we need some form of a constraint that bounds how much the adversary can change its dynamics. All right. To do that, we need to measure a dynamics between we need to have a distance measure between two distributions, because at the end the dynamics are probability densities, right? So now we need some metric in that space, and that metric is going to be, for example, people use KL, Kullback-Leibler divergence. We used Wasserstein distance. That's why we called it Wasserstein Robust RL. All right, and then what happens is that we're going to now assume that, okay, this is our original simulator, and now we're going to be varying, the adversary is going to be varying this phi, right? However, the way it's going to vary this phi should be in such a way that the distance between the new transition and the reference transition, so my original simulator, is bounded by some ball. And that's what this constraint is trying to do right here. So what this constraint is trying to say is that, okay, this is the problem you've seen before, right? So you're going to try to find the best policy under the worst case dynamics, but then we decided to add this constraint. So this constraint is nothing but a ball, but in a probability space, with respect to probability distributions. So it's going to say, okay, I'm going to start with my reference dynamics P0 here, all right? And then I'm going to define a ball around it, such that any variation that the adversary can do, by the way, should be phi, not psi, sorry, typo. Any variation the adversary can do has to lie within an epsilon distance from my original dynamics, all right? So essentially, what this is trying to say is like, okay, look, I want to be robust, but not to any possible change in the dynamics. I want to be robust to potential changes in the dynamics within an epsilon ball of my initial simulator. So what's your initial simulator? Is like the system you're training on. So if you remember my discussion here, I said we trained on this system, right? So this can be your original simulator, let's call it P0. And now you're going to allow the adversary to change, but it has to be bounded with an epsilon Wasserstein ball with respect to P0. Now, for those of you who do not know Wasserstein distances, it's not that big of a deal for now. We can have different talks about that. Just think about it now as some form of a distance measure between two probability distributions, all right? It kind of measures the mass, of how much you want to be able to transfer one distribution to the other. So it kind of considers the geometry of the space. But I will intentionally stay vague on this because that's not the message I want from this paper or from this video. So now you might start asking the following question. It's like, okay, great, we formalized this problem, no problem, great, thumbs up, happy. But how are we going to solve this problem? And let me start by even asking a more primitive question. And that is, how am I gonna model my transitions, right? Okay. So now here's a funny thing that happened to us. We started by trying to model the transitions using neural networks, okay? And then we realized that, okay, this thing doesn't work. And the reason for that is because neural networks are capable of giving you models that only fit data, but they do not reflect physics of the dynamics. So, and now because you allow changes, in the dynamics, then what can happen is you can get arbitrary weird behavior. So we ended up, for example, with a neural network fitting some trajectories from a cart ball that is capable of changing the velocity of the angle without changing the position of the angle. And these are things that are not good, right? So kind of there are two directions if you want to model the transitions. The first one of them is, you would do a neural network, okay? And this is exactly what I just said. Like we ended up, like right there, we ended up with unrealistic dynamics, right? So that's one, all right? And the other one is you can go non-parametric, right? So you can do Gaussian process type of techniques. I mean, they're great, but they do not scale yet to high dynamical systems, all right? So what are we gonna do with that? All right. So I think there are different ways to go, all right? We decided to go in the following way, right? So we decided to go in this direction. We said, okay, look, if you look at Mojuku, if you look at Mojuku or OpenAI systems, you always have some form of a differential equation solver, which you give it a state action, successor state. State action, it gives you successor state. But importantly, right, it also takes a configuration of the robot as an input. So it takes as an input like dynamic parameters, for example, the mass, the length, and stuff like that. So if we parameterize this guy as phi, so we say phi is this input to this differential equation solver, right? Then for any phi we get, we will guarantee that the trajectories we have are based on a differential equation solver which has the equations of motions inside it. So effectively what we will be having as an output is kind of a valid physical transition form of dynamics. So of course people can do that nowadays even slightly differently. Maybe you can use like ODEs, solvers, or there's also this new work by Jan Peters and also Mark Dijsselroth had some work on like neural networks that model physics dynamics. You can also do that. But for us, we thought that this is a more realistic solution towards application on Mojiko. So we went down this road. All right. So the idea here, what I'm trying to say is, in order to model P phi, that's hard. We can do neural nets. We can do GPs. Neural nets gave me unrealistic dynamics. GPs are hard to scale, and also they don't have guarantees to give you realistic dynamics. They are more likely to give you than neural networks, but they are not necessarily giving you also valid physics dynamics. Okay. So then what we said, okay, let's take the differential equation solver that's in Mojiko, okay, and now let's call that phi, and that's kind of the dynamic parameters that we input, and therefore now for any phi we would change, we will get valid dynamical trajectories. But now you should be worried, right? Because now if you think about it, okay, so the point that will happen here is that at the end, if you recall, we want to solve this problem, right? So we want to be able to take gradients, in this phi, right? So we want to be able to, take gradients in this phi somehow at the end, if we're gonna do, a min-max problem, gradient descent or something like this. But now the problem here becomes that, well, if you kind of, did it in the way we did it, right? So if you kind of did it in the way we just did it here, then you will end up realizing that it's very hard to compute these gradients because you want now to compute the gradients in a differential equation solver, which you do not necessarily know up front. We're not modeling that, so it's not like the other techniques that people do, because we're not modeling that. So we do not know it. You can maybe do it using the adjoint method and stuff like that, but we opted to go derivative free for this. So what I mean by that, we were able to prove, and I think. Oopsie, sorry. And I think this is not our result, this first part, but the second part is our result. I will tell you in a sec. But we were able to show that okay, if you are perturbing the dynamics phi, so you take phi, so you can show that the gradient, okay, is actually nothing but this equation. So what is this equation? This equation is you take phi, which is kind of your current dynamical parameters, and then you're going to add on top of that some xi, where xi is a random vector, and that random vector is actually sampled from a Gaussian distribution. So if you do that in expectation and you measure this quantity, then you get an approximation to the gradient with respect to phi. So in our algorithm, what do? We now start by sampling some different xi's, okay? We change this phi parameter by adding xi to it. We pass through this diff solver, and now that gives me some traces, okay? Then I compute this term, or I even Monte Carlo estimate this term, and that allows me to compute an approximation to the gradient with respect to phi. So this is like a zero-order strategy, right? So again, it's not completely ours. The other people have suggested that, but what's ours comes in a second. But now that enables me, to do these gradients, or to estimate these gradients, approximate them without needing, to differentiate in this unknown differential equation solver. All right. So now, given that we got this estimation, all right, let's try to solve the problem. What we had. So we're gonna have a two-step procedure, all right? Because remember, we had a max-min, right? So we had a max-min problem, max over theta, min over phi, all right, of some function of theta and phi, subject to some constraint, right? So that's kind of our problem. I abstracted everything away. But now what we have is we will have a two-step approach. In the first step, we will update the policy. So given a fixed phi, we will update theta. And now given the updated theta, we will update the phi. So we will just alternate like that. We will do like, okay, given a fixed model parameter, apply RL method, PPO, TRPO, in order to get a new theta. Given a new theta, we go to step 2. In step 2, we just update the transition based on that theta, and then we repeat. Now, when it comes to the RL method, that's easy. We know how to apply it and we know how to use it. However, what about the transition model update? Because that's hard, because it has the constraint to deal with. Okay. The way we dealt with that is through approximations. So with respect to phi, we did a first order Taylor expansion to the objective function, and we did a second order Taylor expansion with respect to the constraint. So once you do a second order Taylor expansion around phi 0 with respect to the constraint, you will get this equation. Now, what's this equation? This is again an equation of like a weighted norm, right? So this is just saying that the weighted norm, a Hessian in this case, Hessian weighted norm is less than epsilon, okay? Now, you can see that this is very close to TRPO. Those of you who know TRPO, you will realize that this constraint is very close to TRPO, and it's great. It's good that to be close to TRPO because now we know how to solve it efficiently. But it has some differences, very major differences. The first one, this is not a Fisher matrix here, yeah? This is a Hessian of a Wasserstein distance, okay? And now, interestingly, our Hessian of the Wasserstein distance needs to be evaluated only one time up front and not at every time instant. Why? Because we did a second order Taylor expansion around theta 0. So that led me to H0, which is nothing but H of theta 0. And therefore, if I know theta 0 or phi 0, sorry, I'm using theta here, I should use phi. So H of phi 0. So if I'm using phi 0, then I can compute this Hessian one time upfront and I'm done. And that's the constraint. So that's the constraint I need to solve. And now here, we just did a first order Taylor expansion, okay? And now we can solve this constraint optimization problem, all right? But we still have one problem left, and that is, I told you how we estimate the gradient of with respect to phi, but I did not tell you how do we estimate the Hessian with respect to phi. So for those of you who don't know, a Hessian is like a matrix of second derivatives, yeah, and a gradient is just like a derivative of a vector. And now I don't know if you recall Taylor expansions, but these here equations are not that fancy. It just simply does a first order Taylor and a second order Taylor. That's all it does really. Now, assume we know how to compute the Hessian, all right? Why is this cool? What we did is cool because you can get actually a closed form solution to this problem. Because this is nothing but a quadratic program which can be solved in a closed form, and then the solution will look something like this, right? So by the way, if you look at this equation, you realize this is very, very close to TRPO, right? So here, but instead of the Fishers, we will have these Hessians, right? And I mean, it looks close, you know, on that level, but they are fundamentally doing very different problems. So it's not like doing TRPO. It is. You know, it's like our constraint is a robustness-based constraint. The RPO is just based on the previous policy, what has happened. But so therefore, the remaining step for us, which we wanted to understand, is how can we compute this Hessian? And what we were able to show is we were able to show a zero-order method to compute the Hessian. I think this is new. It has not been done before. But the idea here is again based on just variations of the xi, which is this Gaussian random variable, right? You can actually estimate the Hessian. The way you do it is like this in this equation. So you sample Gaussian vectors, all right? After you sample them, you compute the expected Wasserstein at the change of the original phi plus this xi, and then you compute it on the and then you subtract from it this term right here, right? And then you arrive to the Hessian estimation. So you can do a Monte Carlo estimator of that, and then you get a Hessian estimator. All right. And now notice that what I want to say is that this is not coming out of nowhere. There's a proof of that in the paper, so you can have a look at it and read it. But now we have all the components available for us. We know how to compute a gradient, right? And we know how to compute a Hessian, and now we can run this alternating method. Update theta given a fixed phi, update phi given the updated theta, and then we repeat this process. All right, good. Now I just want to add a word or two on the following. People are talking a lot about the theory of maximum problems, yes. please notice that our max-min problem theory is extremely difficult to get. So game theory people, they do a lot of these works, you know, max-min, min-max type of problems. But they're mostly not using neural networks, and they're not working with non-convex, non-concave settings. There's convexity or concavity somewhere, all right? Our problem is a complete non-convex, non-concave problem, and it's really hard to solve. I just saw last week there were a couple of papers that popped up on this, and in Code this year there was a recent paper on this. So we're reading them to see if we can apply such a theory here. But if you were asking why don't we have theory here, I mean, it's extremely difficult to get theory for neural networks max-min problems. And another thing I would like to criticize others in is that I don't like to do theory just for the sake of theory. What I mean by that is like, okay, if I'm not going to tackle the problem I'm coding, you know, or at least a close enough problem to it, then what's the point of doing the theory, you know? And that's why there's no theory involved here, yes. So let's go to the experiments now. So on the experimental result, remember what I showed you before, right? So I showed you before, like, okay, so we ran this algorithm I just described, and then this is hopper, walker, half cheetah. So these were the tasks I showed you before, and this is half cheetah. You also saw a similar result. Now what happens is you can get this form of improved robustness. So this is again testing, yeah? So this is testing the policy I trained on new environments I didn't see before. Now, a couple of things to realize. Okay, first of all, you see that the red is increased, which means we have a higher reward across these domains. And honestly, this is a state-of-the-art result when it comes to robust RL in high D, continuous states, continuous actions. If you look at our paper, we show that we actually beat a lot of other methods that specifically are designed for robustness as well. But of course, I would like to mention the following, that you don't see any very dark red point here or in any of these systems. And that is to be expected, right? Because if you want to have robustness, you don't want to overfit on one task and do really well. You want to, you know, do well across tasks. And that's why you don't see like an extremely dark point like you see here. Okay. And now we also did this on a higher dimensional setting. So not only on a simple 2D changes of the environment. So these systems, I think they allow you to vary 11 to 15 parameters in their dynamics, if I'm not mistaken. And what we did is we varied all these different dynamics, right? Different dynamical parameters. And then we tested our algorithm. And I think we tested it against PPO, which is also state of the art. So what I show in these graphs is mean reward across different tasks. I think we had 1,000 or 100 tasks. I think 100 tasks. And on the y-axis, we show the empirical density. So i.e., where is the reward mostly accumulated? And now what you can see here is that PPO and has most of the rewards accumulated in this region, which is around maybe 1,000, and a little bit in this region, right? When it comes to even a higher dimensional half cheetah task, PPO is all over the place. Like there's no clear trend. Now, what we did, it's funny actually. So we did two sets of experiments. The first one is we allowed our system to just vary 2 parameters and then kind of transfer that policy and test on high dimensional changes. And you can already see that you can already get from here to here and from here to here. So we're kind of shifting, you know, the optimal reward distribution towards where it should be. And then once we allow the training on all 11 dimensions, right, then we got this result, which says, okay, we are able to, you know, get this robustness in these tasks. Now, again, please note there's no further training, right? You train on one of them, but using our method, and then you test it. Okay. And by the way, I think in the paper you can also find other robustness algorithms. Here I'm just showing a highlight of these results. Now, the other thing I would like to talk about, there's this fancy new hyped thing, which is called domain randomization. Okay, which I think is very interesting and it's pretty cool. But I still don't get why that is not just a naive way of doing robustness. So in domain randomization, what you try to do is you try to kind of maximize over the expectation of the returns. Okay, so here you just have a theta that changes the dynamical system, and here you have a p. Let's call it phi. Sorry. So here we have phi, and here we have p theta, and then you assume that you know, okay, the set of possible changes that you are allowed to your dynamics. Okay. And of course, now it's not naive in that sense because it worked, right? It works really well with robots. But here what we tried to do is we tried to show you that actually having a structured min-max problem that allows you to explore the min direction rather than just doing an expectation over the tasks gets you better results. So here are some of the examples. I would like to mostly note this, right? Because here what we have done is we tested in a high dimensional setting, okay? So the point here is that domain randomization might be very cool, but not necessarily in a lot of allowed variability, because this expectation will have a very huge variance. What we have done is we have tested, on our own, and the way we did it is by varying all 11 to 25 dimensions. And I think this is a Sheta or a half or a Walker or something. But what you can actually see, all right, is that this is the domain randomization result. Yes? So this is the domain randomization result. And this is another domain randomization result. Okay? Now, if you compare this to the previous graph I showed you, you will realize we are, when it comes to high D, we have bigger shifts towards, towards the high reward region. And so take maybe you want to compare this with that. Yeah, sorry, my bad. I didn't put them on the same slide, but maybe you want to compare this with that with that, right? And this with that. And then you realize that, okay, we have a higher reward distribution than domain randomization, okay? And now, why? Okay, I don't know why exactly, but I just can tell you that from my point of view, solving a max-min problem like that, all right, of some function of theta and phi with some constraint, on phi, okay, on phi, theta, phi, is actually much more behaving better or better behaved or well behaved than just doing a multitask version of it. Really, domain randomization is just a fancy word for multitask learning. Again, people redefining terms as is beautiful nowadays. You just do this expectation and another expectation, and then you have a reward, right? So the thing is that this is kind of expectation over potential randomizations, What I'm trying to argue from this result is that I believe this is a better way than doing this, especially in high D, because this allows me to take gradients in which next task I want to try, as opposed to me here pre-specifying the potential distributions of tasks I can look into. And if not, then there's always a variance problem involved. All right. Right, so I will end with this, and I just like to describe this paper a little bit that we worked on. And again, the paper is called Wasserstein Robust RL, and you can have a read at it. If you're interested, please let me know. And again, if anybody is interested in doing things like that, or safety, or model-based RL, just talk to me, because we might have some internship or even open positions for you. Right, so thanks a lot. Next time, maybe we'll talk about another paper, and hopefully we can get some other authors to also give talks other than myself. I'm working on that, bear with me. All right, thank you, and see you soon again.